This video is going to be all about multicast. We're going to be talking about regular any source multicast, that we're going to use a BSR router to assign rendezvous point, and then we're going to take that regular multicast topology. We're gonna split it in half and just make two discontinuous multipass topologies with a regular underlay routing protocol that then we're going to bridge with a GRE tunnel. Over that GRE tunnel, we're going to try to run multicast only. So this will simulate your topology similar to two separate multicast islands running a GRE tunnel or something like an MPLS or an internet, to be able to extend multicast between two data centers or two different POPs. So we're going to first look to see how to do it with static routes to fix the RPF check issue, and then use MP-BGP to do the same thing. So let's go ahead and get started. So I have a pretty simple topology here. We're going to have router 1 and router 2. So router 1 is actually just going to join the group. Router 2 is going to go ahead and send some traffic. Router 3, 4, 5, and 6 is actually are going to be our transit routers for multicast. We're first going to have it configured everywhere. I already have it configured sparse mode on every single link that you see in here. So we'll have PIM neighbors on every single link, and our rendezvous point is router 3 for this particular purpose. So if we come over here and we do we're going to see that I've configured the BSR candidate and RP candidate as router 3. So if we go and look at, as a matter of fact, if I do show IP PIM neighbor, we're going to see that there's neighbors everywhere. If I were to do it on every router, we would see all those neighbors accordingly. Another note on IP addressing scheme, it's pretty straightforward. Every router has a loopback with a router number. So router 3 would have 3.3.3.3 and so on respectively. And the transit networks are all 10 dot lower a number, higher number. As you can see here, it's pretty intuitive. So everything's configured. This is a flat any source multicast topology. From router 2, we should be able to, well, as a matter of fact, I need to join. So if I join the multicast group, oops, forgot to join. What this will do, the second you do a join, it's going to PIM join, so it's going to register with the rendezvous point. So if I come back to the rendezvous point right now and do show IP PIM RP, I'm going to see that registration right here that happened for the 224.222 group. If I do show a PM route, I should see that as well, that it's it put in a star comma G entry for that particular entry there. If we go to router 2 and do a ping, if I can type correctly, this should work. Yeah, so, and it does. It's because it's a pretty straightforward topology for multicast. So if I do show IP mroute over here, I will see that in fact build a star comma G to the rendezvous point, and then it created S comma G entry that's more specific for the shortest path 3. So everything works correctly. And kind of reminder for multicast, obviously there's two things going on. When somebody joins a group, that's a control plane change. It's going to register with a rendezvous point. When somebody sends any traffic for that group, that's a control plane change to where it's going to enter this S comma G and star comma G entries after that traffic gets to the rendezvous point. And so, and that's one big thing about your regular any source multicast with a rendezvous point is it generates a lot of control plane modifications throughout your multicast lifecycle. So if you have a lot of groups, a lot of joins, a lot of different senders for the multicast, it could potentially be in a stable environment, depending on that. That's why you have something like bidirectional PIM and source specific multicast to fix those issues. Kind of outside of this lecture here, but worth mentioning anyway. So what we're going to do now is we're actually going to break the connectivity here. So I'm gonna make the R3. I'm actually just going to kill the sparse mode on those interfaces on interface 2 and 3 right here. So I'm gonna come over here. Interface G2, no PPIM, sparse mode, interface 3. Same thing. I'm going to do the same thing on R4. So these two interfaces, I'm going to kill PIM on them as well. So, and then I'm going to go ahead and do clear IP mroute start just to clear the route. And from this perspective right now, we have completely disconnected multicast. So if I come over here to router 2, unless the route, yeah, I just cleared the route, so it should not work. Oh, I guess the route is still cached on these guys. I did clear it, but on router 2. So well, let me give it a second and clear it everywhere. So obviously, just because the PIM dropped doesn't mean that the data plane has dropped. So it might take a couple of seconds for it to actually time out and go ahead and disappear. So let me go ahead, and while it's doing that, I'm going to create a tunnel because it's still not going to work with the tunnel in place without anything else preventing the RPF issue. So we'll go ahead and build the tunnel. So on router 4, again, we're going to use 100 instead of 10 for the tunnel. So 103.4.4 is on the 4 side. I'm going to go ahead and build the tunnel on the 3. So all I did right here is I created a direct tunnel between this router 3 to router 4. So and I'm gonna, as you can see here, I'm running PIM sparse mode. So once it comes up, it's going to create a PIM identity directly across this tunnel. However, I'm not running OSPF on this tunnel, so all the routing is going to happen on the underlay. So then we can validate this right now. So if I do show IP route, I'm going to see that I have no routes going over the tunnel, obviously, except for that local /24 network. And that is on the tunnel. So let's see if we can make not MPLS, if we can make multicast go over that. So we can validate this should not work, and it doesn't. So the reason why it doesn't work is obviously now our RPF is failing. One step further, we should not even see an RP on router 4, because what's going to happen when router 3 advertises the rendezvous point advertisement over this tunnel link between R3 and R4. When it gets to R4, the rendezvous point, which is the loopback address 3.3.3.3, is actually failing the RPF check over the tunnel, because when it comes in over the tunnel, it says, well, no, I actually can reach 3.3.3 over the underlay. So that's your first RPF failure. So if I come to this R4 and I do to show IP PIM RP mapping, there is no mappings here. So as you can see, it's not working. One step further, if we want to wait for the debug message, PIM is not the fastest protocol, but we can do debug IP PIM BSR in this particular case. And if we wait for just a couple of, hopefully not minutes, I mean, depends where in the cycle. Oh, we got lucky. So perfect. So it tells us right here, it's trying to register 3.3.3 on an RPF path. And here's a neighbor. So that's why it's failing. So the first thing we're going to do is we're going to fix this RPF check failure for the rendezvous point. How do we do that? Well, it's very easy. IP mroute, we'll do the statics first. 3.3.3.3 mask. So as long as it obviously covers this specific case, we only care about the /32 route, and we're gonna create the RPF neighbor. That's what it should be. So in this case, we're just gonna say, hey, don't use OSPF to figure out where your RPF neighbor is, which is, well, not OSPF, but whatever the routing table says. Use this mroute entry that says, hey, when somebody registers one rendezvous point, this is the RPF check for it. As you can see right now, it just came up. If we do show IP PIM RP mapping again, we can see, hey, this is our rendezvous point for 224.0.0/4. So that fixed that first issue. Obviously, when we send the traffic from R2 down to R1, the same RPF issue is going to happen on R3. So when R4 sends it down the tunnel, R3 will receive that traffic from R2, and it's going to say, well, no, it actually is supposed to come down one of these other two links, since we're not advertising anything over the tunnel link. So we're going to need to fix that. So even though we have rendezvous point fixed, as a matter of fact, this is kind of a unique scenario, because even it actually should work right now, because it's just going to send it to rendezvous point in the absence of the actual S-G entry. So let's validate it. And if it works, again, it works just because of this topology. If a rendezvous point was anywhere else except for here, it would not work. But we can validate it also with going to R4, and I just pinged from R2 all the way down to R1. But if we go to R4, we should not see a correct S-G entry in the routing table. So if we look over here, you can see an S-G entry for it, but it says registering and outgoing interface is null, so it's not working. So all it's doing is actually sending it to the rendezvous point, and then when it gets there, it sends the rest of the way. So but let's go ahead and fix that as well. So how do we do that? We'll come to R3, same thing, IP mroute, and that's going to be the source network, which is 10.2.4.0. 100.344 is where it's supposed to come from. So now if I come over here, let's repeat it 10 times or something, just give it some more traffic. So it still works, but now let's come back over here and look at our S-G. Obviously, it looks a lot better now. So we are on the shortest path 3. We're using the tunnel interface as I'll go on interface list. Yeah, this looks a lot better now. So this fixed our entire issue there, and that's with the static routes. Obviously, static routes is not scalable. You can do the same thing with MP-BGP. So let's look at that. So first, let me go ahead and take out the static routes. Obviously, static routes a lot easier than MP-BGP, as we're about to see in a second. So let me go ahead and paste this in, and I will explain exactly what's going on here. So what we're doing is we create, 65,000 as the regular private autonomous system. We're going to say, hey, this is our namer, remote AS, same AS, so it's going to be IBGP, nothing fancy here. We're turning off the regular IPv4 address family because, well, we don't need it. We're only going to use the multicast. We're going to come in, we're going to activate this neighbor for the IPv4 multicast family. And then what we're going to do is, and for good measure, I went ahead and put in this network in there as well. So this is for our rendezvous point. So this router 3 will advertise to router 4 the 3.3.3 address. So that when router 4 sees the rendezvous point register over the tunnel, it's going to see it as an entry from the BGP table, and it's going to do exactly the same fix as the static mroute. This, I put it in there just because this is the network on R1 and R3, so the same thing happens there. Now let's actually, I am missing a couple of things which we're going to see an issue here in a second that I'm going to have to fix. Which is fine. So let's go ahead and do it on this side. Same thing, we're pasting the neighbor. And that's the issue I was talking about. On this side, I put in the distance for the administrative distance. On the other side, I did not put in the distance for administrative distance. We'll see what problem we'll create. So see, it's still complaining that RPF is failing. No worries, because BGP is not the fastest, probably not up yet. So the neighbor came up, but the advertisement take a minute to actually propagate. Show BGP all. So we see, so actually do see 10.2.4.4. So that's our local injection on R3. Let's see what's going on here. These are our local injections as well. Okay, so now we see that the routes have propagated. On this side, let's look at 3. So that's what I was talking about. You see that it's got a rib failure right here, so it's still not going to work. That's why we need that administrative distance, because this is still the IBGP is worse than an OSPF. So I need to go ahead and fix that. So let me go ahead and change the distance BGP, external, internal, and local. And I am probably gonna have to bounce this connection for it to actually take effect. So I'll give it a second to actually get it. So we see the neighbor bounced. I wonder if it got a chance to register the rendezvous point before it fell down. I don't see it. That's fine. It'll come up in a second. So as you can see, it's still complaining about RPF check. That's because where we set the BGP neighbor, it's still waiting for the advertisement for 3.3.3.3. Like I said, BGP is not the fastest protocol. It's built for the internet, so it's taking stability over speed all the time. So here's our advertisement, and as you can see now, this fixed the rib failure on this side as well. So now we should see show RP mapping. Let's see if, oh, okay, so it's already, I missed the message, I guess, that said it came up from the debug. But it is, you can see that rendezvous point is in fact advertised through PIM, so that passed that RPF check. Coming this way for rendezvous point. Now if we come to router 2 and try to ping this 224.222 on this side, it should pass the RPF check on router 3 side, because as you can see here, this 10.2.4.0 network has the proper next hop. which identifies where it came from the tunnel on this side. So let's validate it and make sure it doesn't make a liar out of me. Come over here and we should be able to ping without an issue now. And we can. And that is all the cases for MP-BGP and the static mroute. All right, until next time.